Okay, we continue the discussion of Lagrange methods or Lagrange algorithm. Again, recall that we first form the Lagrange condition for a optimization problem with equality constraints. So this is what we're trying to solve. And then we first form the Lagrange function, and then we'll get this f of x plus hx transpose times lambda. This is the Lagrange function, and then we take the gradient, get the Lagrange condition, which are these two, right? And then we form this Lagrange algorithm. This is what we discussed last time. Okay, so we said that if the sequence converge, it's very likely that, or at least it looks very promising that the limit point will be a Lagrange point. The reason is, as we said last time, if we can show the sequence generated by the Lagrange algorithm in this way, then by taking the limit on both sides as k goes to infinity, we will be able to see that the limit point x star and lambda star will satisfy these two conditions. Right? This is what we discussed last time. But today, in this lecture, we're going to show that this is actually the case. If we started from somewhere really close to the KKT point or Lagrange point, and there's a special property for this point, which is the we call that the Hessian we defined earlier. If at this point x star lambda star, this Hessian matrix, which is only the Hessian with respect to the x, if this point, this Hessian matrix is positive definite at the point x star lambda star, then when we start from somewhere really close to this x star lambda star, it's guaranteed that it will converge to this limit point. Okay, so this is what we're going to show here. Okay, so first, give several notations. Right now we have this x as the solution we want to get, and this lambda, which is a Lagrange multiplier, and this is an n-dimensional vector. This lambda is m-dimensional vector, where m is the number of equations in the constraint, right? Which is the dimension of this, okay, or this. Now we can form this function. We call it the u of w. So now this w is the n plus m dimensional vector, and we're going to form a function. U is a function of w, and this function is a scalar valued it's a vector value rather than scalar value. And this u of w will be another vector, which is also n plus m dimensional. Okay, so in other words, this u is going to map a vector in this space to another vector in the same space. And what happens is that it will take any w, and w is this n plus m dimensional vector here. You just concatenate or you paste this variable x and the multiplier lambda together to form a longer vector. And this is what the w is. And this u will take this w to u of w, which is also n plus m dimensional vector. And what this vector exactly is defined in the following way. Because this w contains both x and lambda, so this u of w should tell how do we do with this x and w, x and lambda, or how do we do the component in this w. And what it does is it will form two vectors. And again, once they have these two, we get these two vectors, we will paste them together or concatenate them together. So the first vector is defined in this way. So it's not tricky at all. It's just the x itself minus alpha, which will be the step size. And this part is exactly the Lagrange condition, the first Lagrange condition. Okay, as you can see here, or this one. Okay, This is just to this is just going to give us a very simplified notation to write down this Lagrange algorithm. Okay, and to do that, the first one is just the Lagrange condition. The second one is the second Lagrange condition, which is the hx equals 0. And what is different right now is that this is alpha, this is also alpha, and this is x, this is lambda. So why we're doing this is because recall that the reason this conceptually was the reason why we got this Lagrange algorithm is kind of doing the gradient descent of this Lagrange function with respect to x, right? So this is pretty much like the, as we said last time, which is pretty much like this, minus equals to xk minus alpha, which is a step size gradient with respect to x, L of xk lambda k. This is exactly the same as this one right here. And similarly, we're going to get the second one, which is just this plus alpha times gradient with respect to lambda of this one here. Okay. So this is the why we give this definition here, and it will help us to simplify the notation we have for the Lagrange algorithm. Okay, because for this, we can just see that when we plug in w equals to wk, or x equals to xk, lambda equals to lambda k, that is exactly the right hand side. That's exactly the right hand side. So this whole thing here is just that the u of wk, where this wk is contained or is composed by the xk and the lambda k. Okay, and this is the right hand side. The left hand side is just the u. This side is just the u. Just the w. Sorry, just the wk plus 1. Okay, so that's the purpose of introducing this u function, because it just tells us that the Lagrange algorithm is doing nothing but wk plus 1 is equal to u of wk. Okay, why? This is going to help us to show that this algorithm is going to be convergent, because as you can see, if we can show that by doing this by doing these iterations, if they get convergent, then this w star, so if the left-hand side converges to w star, the right-hand side is converging to u of w star. Okay, and once we can show this, we'll be able to show that the w star is a Lagrange point. Okay, so the only thing we need to do is to show that this u, by using this u, we'll be getting a sequence that converge to that be convergent, and the limit point will turn out to be a KKT point. So we'll see that soon later. But right now you can see that this Lagrange algorithm is doing nothing but just the one we showed. It's just the wk plus 1 is equal to u, is set to u of wk. Okay, so to show that, we have to do some preparations. We need to check the property of this u. Why it is going to give us, call that, we got this wk plus 1 equals to u of wk. So we start from some w0, and we'll give a condition for w0 or w0. It needs to be somehow close to the true solution or to the limit point, and then we start from there. Then by iterating this, we'll be guaranteed that this wk will convert to the limit point, to that limit point. Or in other words, say we have a w star. Remember, this w star always contains, is just composed of the x star, lambda star, which is a KKT point or Lagrange point. Okay, suppose we start from somewhere nearby. Say, or my W or W0 was started somewhere nearby this W star. Then we can just check the property of this U function, and then we will be able to show that by generating the sequence starting from the W0, we will get a sequence of points that converge to W star. Okay, so that's our goal. Okay, so the key is that why this U can give us this property. What is special about this U? Well, the U, since we defined it in this way, we can check its gradient, or in this case, actually the Jacobian, since this U is a vector valued function. So taking the Jacobian of this U is nothing but, remember that we have the gradient of U of W. And on the one hand, we know that this W has two components, X and or two is paced up by two vectors, X and V. The other thing is that when we take the gradient, we should take gradient with respect to the X and lambda separately. So it's gradient of U with respect to X, of U X lambda, and then also the gradient with respect to lambda of U X lambda. Remember that this U is a vector valued function. Okay, so when we take the gradient, it's actually the Jacobian. So we're expecting to get, since it's from Rn plus m to Rn plus m, we're expecting to get expecting to get a square matrix of size n plus m by n plus m. Okay, so let's see exactly what that is. So to do that, we just need to take the gradient. This is the first part. We need to take the gradient with respect to x. Now you can see that when we do that, we'll get identity here, because when we take the gradient of x, it will become identity. And then take the gradient of this, it becomes the Hessian of f. And then gradient of this is what we said last time. When we take the gradient of this, it becomes this part will become a n by n by m matrix. And then we multiply this m-dimensional vector, we will get a n by n matrix as a whole. Okay? So that's what happens on the first row. Let me write it down. So this is going to be I minus alpha of the Hessian plus the d squared h x transpose lambda. Okay, so that's for the first part. The second part, we need to take the gradient with respect to lambda for the second part. And as you can see, what we'll get is just I'm sorry, so it should be this. I haven't finished the first row yet. So the first I should write in this way. I shouldn't do this. So I need to do this. So gradient of, let me just directly write down what I should have here. It should be, since I have U made up by these two components, this and this, so my Jacobian will be the gradient of this with respect to x, and then the gradient of this with respect to lambda. And then I put these two on the first row of this 2 by 2 block matrix. And then I'm going to take the gradient of this with respect to x, and then this with respect to gradient of this with respect to lambda. And then I'm going to put it as the bottom row of this 2 by 2 matrix. So this gradient, this Jacobian of this should be a 2 by 2 block matrix. And the components is what I just said. It should be I minus alpha gradient Hessian of f plus d square hx transpose lambda. So that's the first component, the first block. The second block will be the gradient of this with respect to lambda. That's going to be my second component here, our second block here. So as you can see, when I take the gradient with respect to lambda, what I will get is simply negative alpha times this. Okay, so that's what I have. And similarly, we're going to get the bottom blocks. So we're going to take the gradient of this with respect to x, and as you can see, what I get is alpha times the dh at x. Okay, the gradient of that is just alpha times dhx. So, and then finally, I'm going to take the gradient of this with respect to lambda, which will be identity. So that will be the identity matrix. Okay, so now you can see that we have a diagonal matrix, identity matrix, and identity matrix here. So I pull it out. So I make a sum. I can decompose this 2x2 block matrix into two matrices. One matrix is just identity matrix. You just get this, and then I will extract the alpha. What is left over, I actually extract alpha, and then what is left inside will be just a negative of this. That's the first component, and then negative of this, that's the second component, second block, and then this as the third block, and 0 here because we extracted the I outside. So that's why this is just this one here. And we have the I part, and we have the alpha times this matrix right here. And this one is just the Hessian of L with respect to x, as we introduced earlier. Okay, this is how we got the Jacobian of U. Okay, so why this Jacobian is going to help us? We're going to show that the Jacobian matrix here has a will guarantee that this one will generate a convergence sequence when W is close to, or W naught is close to W star. Okay, so this is what I'm going to show soon. First of all, let's remember that we have showed that if we do this, iteration and they converge, this converge to W star, this converge to U of W star, then it is pretty easy to show that this W star is a KKT point, or is a Lagrange point. Okay, and actually, in this case, we call the W star a fixed point of U, because we'll get W star, or we'll get this. Okay, so W star is a fixed point of U, meaning that this is true if and only if this W star is a KKT point, or is a Lagrange point, and you can easily show that. This is what we have said last time. Right, you just take a limit, and you realize that the W star will satisfy the condition. Satisfy this condition. Okay, so we're also going to denote this part. Say, since we're going to show that the sequence generated nearby, starting from somewhere nearby, the W star is going to converge to W star. So we need to tell that the W star should have some kind of be attractive somehow. It should have certain properties so that the points nearby can be attracted to him. Okay, in how this attraction is defined, we need to make sure that the matrix M, defined as this matrix evaluated at x star lambda star, is good enough. We'll show how do we mean by good. So by this now, if this x star lambda star is a KKT point, then we can define this associated matrix M by evaluating this matrix at the x star lambda star, and that is your M. That's your M. Okay, so the gradient, the Jacobian of U at W star is nothing but I plus this alpha M. Okay, there's a very important structure in this M. You can see that this is 0, pretty simple. This is a Hessian matrix, so it is supposed to be a symmetric matrix, and we have a negative in front of it. And then this DH transpose is the transpose of that. Okay, and the only difference between them is that there's a negative right here. Okay, so first of all, what is this matrix matrix. This is the same size. This matrix is the same size as the Jacobian, which is n plus m by n plus m. Another thing is that this will be the top left n by n matrix. So this is n by n. And then this will be n by m. This will be m by n. And this is m by m. Okay, so this is how this is constructed. So say we have, basically we have this matrix, and say m is less than n. It's often less than n, right? Because we have this equality constraint. The m is less than n, since that this is the common case, especially when we consider linear constraint, hx equals to ax minus b. We know that a needs to be has a full rank, so m has the number of rows in A is smaller than the number of columns. So this is the n, this is the m, sorry, this is the n, this is the m, this is the m. Okay, so this is what each part of this looks like. So this is actually here, and this is actually here. Okay, and this is the here, and this 0 is right here. Okay, so that's what this m is. Okay, now what kind of properties we need for this m to be half, or for this x star lambda star point is to be good? Okay, so the idea is that we need to make sure this matrix M, all the eigenvalues, or all the positive part of the eigenvalues of M must be negative. Okay, so here is a tricky thing. This matrix, first of all, this matrix is not symmetric, because we said that this is just this is the negative of this transpose. So this matrix is not symmetric, although this part and this part are symmetric, but the off-diagonal blocks are not symmetric to each other. So we are not guaranteed that this M, all the eigenvalues of M are real. Right? We know that if the M is a symmetric matrix, then we can guarantee that all the eigenvalues of M are real numbers. But if it's not symmetric, then we don't know that. But it must have eigenvalues, just that the eigenvalues could be complex valued. There could be complex numbers. Okay? But no matter what we're going to show is the eigenvalues of M, even if they are complex, their real part, the real part of the eigenvalues of M must be negative, must be strictly negative. We need to guarantee that, and that will help us to show the sequence will be convergent. And to show that, the only thing we need is to guarantee that this matrix is positive definite. Okay, as long as we can show this is positive definite, it is sufficient to show that this M, all the real part of all the eigenvalues of M are negative. Okay, now let's see why that's true. Okay, so I think I have the additional negative here. Okay, so we are going to make several claims. The first one, I think the first one here is the most difficult one, the most technical one. The other ones are pretty easy. And these claims, the series of claims that we make here, will help us to see why the sequence is going to be convergent. So the first claim we're going to make, remember that now, since we're trying to study the convergence of the Lagrange algorithm, or more specifically, the local convergence of that, meaning that we need to make sure that we started from somewhere really close to W star, and then we can guarantee the convergence. This is in contrast to the more ideal convergence, which is known as the global convergence. So when we say algorithm is globally convergent, means that it doesn't matter where you start with your initial guess, it will always converge to a solution. So that's the most ideal case, which is called global convergence. But right now, we can only show local convergence. It's not as good as global convergence, but it's better than nothing. Okay? And that's what we're going to show here. And actually, the only thing that we can show here. We cannot really show the global convergence. And that is a common issue with with the general optimization, especially when the problem is not convex. It's extremely difficult to show the global convergence. Okay? The local convergence is probably the best we can get. Okay, so here we're going to assume that the step sizes are constant at alpha, and then we're going to make the first claim. The first claim is that if our step size alpha is sufficiently small, so the step size appeared here. So we said the alpha k, beta k, they're both the same, as we said, and they're all set to a constant value. And if this constant value is not too large, then we can guarantee that this is less than 1. So what this one is, this is the Jacobi matrix we just said. It's n plus m by n plus m. And this right here is the norm, matrix norm of this matrix. So what do we mean by a matrix norm? You can basically think that as the now let's say that if you have a say that. So I have a say I have a matrix. I call it say A. This is a square matrix. The norm of A is the maximum of that, where x is in Rn. So if A is n by n, then the matrix norm of A will be that. Will be this, defined by this. Okay, so this is called the matrix norm, induced by the norm of vectors. Since for a vector, we know perfectly what the norm is. So we don't know what's the norm of A, but we can define the norm to be this, where the denominator has a norm of x, the numerator has a norm of ax, which are both vectors, right? This is both vectors. So we take norm has a precise meaning, and then we take the maximum value we can get by looking through all these x. That value is called the matrix norm of A, and this is called the induced norm, because it's induced from the vector norm. Okay, and the property of that is if you have any vector x, this must be less than or equal to the norm of A times the norm of x. Okay, these two are vector norms, but they are norms of vectors, and this is the matrix norm we define. And this is obvious because the way we define the matrix A. Right? And it definitely implies that this is true for all the x. Okay, so this is what the matrix norm is, and it's the geometry. What it means, I think I mentioned this somehow before. Geometry, what this means is that if you have, say, my A is a 2 by 2 matrix, and then we'll have a unit circle here or unit disk here. 1, -1, 1, -1, this is x1, this x2. It will apply the matrix A. It will stretch this ball to a new shape, likely to be a ellipse. So the AX, the norm of A, so let's say we stretch it to this shape, or whatever shape is the ellipse. When this length right here, so we'll apply the matrix A to the points in this ball, we'll get an ellipse, and the longest radius of this ellipse is called the norm of A. So this length here is called the norm of A. Okay, so that's the matrix norm. And actually, if we can show that the largest eigenvalue of this matrix, this Jacobi matrix, is less than 1, then it will be sufficient to show that this norm is less than 1. So we'll see that soon later. Okay. So now let's look at the how to show this claim. It will be sufficient to show that the matrix right here the real part of all the eigenvalues of this matrix is less than 0. It's negative. As long as you can show that, it will be easy to show that this is less than 1. Okay. Then how do we show that? Well, the idea is that suppose we have some eigenvalue of m, and this eigenvalue means that we can find a w, which is written as the concatenation of x and lambda. Is the corresponding eigenvector, and in this case we know that mw will be equal to lambda w. Right? In this case, we say that the w is the eigenvector of m, and the lambda is corresponding eigenvalue. And what we need to show is that this lambda must have negative real part. Okay, and remember that w could be a complex value vector, but it's composed of two parts, x and lambda. And as an eigenvector, it cannot be 0, right? There's no way. Eigenvectors must not be 0, and we're going to show that if our eigenvector is this, then the x cannot be 0. Otherwise, this w will be a 0, which contradicts to the fact that w is the eigenvector. To show that, let's look at the case. If x is equal to 0, what will happen is that this mw will be m times w, which is 0 lambda, right? Which will be 0 lambda. And this will be equal to lambda. This lambda is the eigenvalue right here. Sorry. This lambda, this bold-faced lambda. This letter lambda is the eigenvalue. This lambda right here, which is bold-faced, is the multiplier we have associated with x. So there are two different things, totally different things. You can use a different notation for lambda for eigenvalue here, but just remember they're different. All right, so this m, let's recopy it. This is the M matrix as we defined before. And this W is going to be 0 lambda. This lambda is a multiplier, remember that. The x is 0. Okay, now when we multiply these two together, apparently it's going to be this matrix. It's easy to show that. Okay, and the denominator, the second block is just 0. And this is going to be equal to the eigenvalue lambda times the W, which is going to be lambda times 0 and this lambda. Remember that these two lambda are different. This lambda is the eigenvalue. This is the multiplier, the Lagrange multiplier that we had before. Okay, this is scalar, but this is the vector. But anyway, that we will get this. If x is equal to 0, we will get this. Well, if this is 0 means that if we get this, that just means that this one is equal to 0, because it will be lambda times 0, so it's just going to be 0. This is 0, and well, if it's 0, we will see negative of this matrix, which is DHX star transpose times lambda, which is the vector right here, is going to give us 0. So I don't need the negative here. It doesn't matter, negative here, but this will be equal to 0. However, if we assume that x star is a regular KKT point or regular Lagrange point, meaning that the DH has a Fourier rank. DHX star is Fourier rank. Okay, then this means that x star is regular. If this is the full rank, and now I took a transpose of that, so this becomes the transpose of DHX square. So it has full rank means that it has a full column rank here. So the columns here are linearly independent. Okay, and if we have a linear independent matrix, the vectors are linear, columns are linear independent, and we multiply it by lambda, we get 0, and that means the lambda must be 0, because this times lambda is essentially just making a linear combination of the columns in this matrix, and the coefficients are given by lambda. But since these columns are linearly independent, the only way to get 0 is that this lambda is 0. So that means this lambda or this lambda is 0. Well, now we show that if x is equal to 0, the lambda is also equal to 0. Okay, and this means that the w vector is 0, and that is contradiction to the fact that the w is an eigenvector. Okay, and from here we can claim that there's no way to have the x equals 0. So if w is an eigenvector of this matrix M, then the x part cannot be 0. Okay, if it's not 0, then we can see a very interesting result. When we do this, we compute this WH. This is the Hermitian or is the complex conjugate of the vector W. Remember that W is a complex valued vector, or is a complex vector. So this means that we're going to take a transpose, conjugate transpose of W. So we're going to change the shape, but also apply a conjugate of the complex values in the components of W. And then we're going to multiply this by M, and then W again. Okay, so on the one hand, we know that this is equal to, because W is the eigenvector, so this is just equal to the lambda times WH times W. Okay, we extract and put this lambda outside. And then, because these two must be equal, and then we take the real part will be also equal. Okay, but for the right-hand side, these two together, we know that if we have a complex valued vector and take the conjugate transpose with itself, it's like taking inner product of W with itself, we will get the norm, squared norm of W. And in this case, what does it mean is we have W1, say W1 is Wn, and they are complex valued. And then the W Hermitian of W, this is actually equal to the sum from I from 1 to n, and Wi conjugate times Wi, right? Because this first one gives us this row version of that, but then also need to take this one is actually the row version of W, and also need to take the conjugate for each one of them. So that's how we end up with this. And this is going to give us sum of I from 1 to n and Wi squared. So this is actually the magnitude of the complex value Wi, and then square it. And this is just the norm of W squared. Okay, it's like the norm in the complex space, and the complex space Cn. Okay, select the norm in here, but the meaning of that is the norm. Okay, so that's why here we're going to look at this to be the W norm squared, and it's definitely a real number, right? So you multiply a real number to a potentially complex number here, the real part will be just this number times the real part of this lambda. So that's why we got the real part of lambda times the squared norm of W. Okay, that's what happens on the one hand. We'll get this. And now let's check this one more time and see what this one actually is. Okay, we'll see something interesting because of the structure of M. Remember that this W again is WHMW is equal to the X H and the lambda H. This is what the two parts of W are. And then we take the Hermitian of that. And this M, remember that it is negative Hessian of L at X star W star. So let me complete that. It should be X star lambda star. Okay, and then we're just copying what this M is. Now here it should be negative DHX star transpose, and then we have DHX star, then we have the 0, and then it will be going to multiply H, X, and lambda. Okay, and after you do that, you realize that this is nothing but just this part, and this part multiplied together. So that will be X Hermitian gradient X square L of X star lambda star, and then X. And then we have this negative, so we still need to keep it because this negative appeared here. So I need to still keep it. Well, what is the reason? The reason is pretty simple. Suppose we have, say, X transpose or Hermitian, lambda Hermitian, and we have this matrix, say, A, and we have this negative B transpose, and this B, and then 0. So this A right here is this. Okay, and this B or this B here is the Jacobian of H with respect to X star. Okay, so it's actually just this matrix. That's the B. And this part is just negative B transpose. And then we have the 0. And we see that this is actually giving us the X part, the lambda part doesn't matter anymore. Okay, and why is that? We can simply just do computation. Okay, let's first multiply the last two together. What we will end up with is AX minus B transpose lambda. Okay, and the bottom row is giving us BX. Okay, now let's see that we multiply transpose, we make computation again. So this will be XH, AX minus XH, B transpose lambda. Okay, that's what happens when we multiply X transpose or XH to this. And then we're going to add this times this, which will be lambda H BX. Okay, will be this. Well, you see that this last two terms will cancel. They will cancel because this lambda HBX, you treat this as a vector, complex value vector. This is like the inner product of these two, right? And this is the same as you take the BX Hermitian lambda. And this is just giving us X Hermitian, B Hermitian. B Hermitian is like is the same as B transpose because B is a real valued matrix. So the Hermitian is just the same as transpose, and then we have the lambda. And that's why this is equal to that. And that's why this is equal to that. And they will be cancelled. So we just cancel them. And what we have end up with is just this one. Okay? And that will be just the X transpose times the matrix A, which is this negative of this. That's why we have the A here. And then X. Okay? So that's why we got that. Well, once we get this, since we assume that this matrix is positive definite, so that's why you take the real part of that. It's definitely going to be greater than 0. If X is non-zero, then this has to be greater than 0, since this is a positive definite matrix. And then we have a negative outside, so this makes this thing negative, less than 0. Well, now we did compute this. On the one hand, it is equal to that. On the other hand, it is equal to this, which is negative. So that just means that this is equal to this, which is negative. So these two are equal, and they are both negative. Well, this is negative. Look at this. This must be a positive number. And if the product of the two is negative, that only means this is negative. And this shows that the real part of this lambda must be negative value. And we didn't specify which eigenvalue we used. We just said that for any eigenvalue lambda, we end up with showing that the real part of this lambda is negative. Okay. So this finishes the first claim. Well, just one more thing that we show that the real part of the lambda is negative, or for any eigenvalue of m, the real part of the eigenvalue is negative. And then we can show that this is less than 1. The reason is, let's show all the eigenvalues of m on this plane, on this complex plane. So this is like the C. Well, if all the lambdas have negative real part, that means all the eigenvalues of m will be something like this on this side, on the left-hand side. Well, in this case, if you say you multiply lambda, you multiply this matrix M by alpha, then all these eigenvalues will be scaled. Scaled meaning that, say, if you multiply if you consider M itself, these are its eigenvalues. And if you scale this M by alpha, then say alpha equals to 2, then for example, this point will be scaled to here. And this point will be scaled to here. Okay, but if you choose alpha to be very small, then they will be moving towards the origin. You get closer to origin. Okay, so when you choose alpha extremely small, then it's likely that all the points are somewhere just near a very close nearby neighborhood of this x. So let's just say that it could be just somewhere here. Okay, I'll say that. So when alpha is extremely small, all the eigenvalues will be inside there. Okay, let me erase that. So all the eigenvalues, so these dots are eigenvalues of alpha m. And then you add identity matrix, then that will shift the eigenvalues by 1. So it will be, say this is the 1, you will shift all the eigenvalues to somewhere here. Okay, but it's still on the left-hand side of 1, of the vertical line 1. Okay, and this shows that the real part are always less than 1. And this is sufficient to show that this the matrix norm is less than 1, because you're not going to scale this. So all the eigenvalues will be just around here. And when you have a matrix with all the eigenvalues just less than 1, then there's no way to, the 2 norm must be less than 1 as well. Okay, this is the property of the first claim we just made. Okay, so that's one thing. That's the first claim. The second claim will be easier. If we know that, say this is the W star, and this is the ball. Okay, if we know that at the point W star, the Jacobian U at a W star has a norm less than 1, then we know that in the neighborhood of W star, all the norms are less than 1, because this Jacobian is a continuous function of W. So if it's, the norm is less than 1 here, then it will be less than 1 in the neighborhood. Let's say that this is the neighborhood of W star. You will pick up any point W from there, you'll be able to show that this is less than, this will be less than 1. So not just less than 1, say this number, what we got this for this number is, say, 0.7. Then in the neighborhood of that, all the gradient, all the Jacobian in the neighborhood will probably less than 0.8. Okay, you can always just to make this ball sufficiently small so that all the values will be less than some number strictly less than 1. So let's say that number is kappa. So that's the point. The kappa is 0.8, as we said, as we made as an example earlier. Say we know there exists some kappa like the 0.8, so that within this neighborhood, all the points W will have a gradient, or will have a Jacobian with the norm smaller than or equal to kappa. Okay, as long as this is less than 1. Okay, it could be pretty close to 1, but as long as this is less than 1, say even is 0.9, then we can say that there exists some kappa equals to 0.95, such that this is true. We just need to be smaller than or equal to kappa, which is strictly less than 1. That's what we need to use to prove the convergence. Okay, so what we're going to make the claim here is that if the there exists some eta, which is the radius here, sufficiently small such that, and also the kappa here, which is between 0 and 1, like the 0.8 or 0.95, which is mentioned, there exists such two numbers such that within this ball, all the Jacobians at all the points will have a norm less than kappa. Okay, and the proof is pretty easy, just by following the fact that the Jacobian of U is a continuous function. Okay, then within the neighborhood, the norm must be all less than kappa, where kappa is strictly less than 1. Okay, so that's the second claim. And the third claim will be the final claim we want to make. We're going to show that if we started from some W naught in this neighborhood, so this was the neighborhood we decided, so this is the eta. If we start from W naught, then it's guaranteed that by iterating the Lagrange algorithm, this W naught will converge to W star. Okay, and to show that, the claim, what we need for the claim is that if it's initially in the ball, then for all the k's, we'll have this less than that. So what this one is, this is the distance between WK and W star. This will be the distance between the next iterate, WK plus 1 minus W star. And this shows that the distance will be bounded or scaled down by kappa. Okay, remember that if your kappa is 0.8 or is 0.95, as long as it's a number less than 1, then the length here must be smaller than the length here. Okay, because it's scaled down by kappa. And if you can continue doing this, then you can see that every time we scale it down by kappa, and the kappa is some number less than 1, so eventually the kappa will help you to decrease this. Eventually this one will convert to 0. Okay, so that's a common, pretty obvious fact. Okay, the question is, how will we show this? How are we going to show this is less than kappa of this? Because the idea is pretty simple. We just need to define this new function g, which is a mapping from W to a matrix. So it takes some W, and it will map to G of W. But this G of W is actually a matrix. It's n plus m by n plus m matrix. What this matrix is? Remember that you can always say we have a function f x. We know that by mean value theorem, we know that there exists some point for any x and any fixed x star and any x, there exists some point between x and x star such that this is equal to f prime at say c in the x minus x star. Okay, so this c, the kc is between x and x star, or x star x, doesn't matter. Right, this is the by mean value theorem. If this is f, it's just a scalar valued function. Well, we're just extending this to the vector valued function, where we have this u of w equals to the u of w star will be equal to the Jacobian of u at c and w minus w star. Well, this c is not a scalar anymore. It's somewhere between w star and the w, which are the w maybe is here, w star is there, w is there. So your The C is somewhere in between, but this is not a scalar. It's some vector some point in between. Well, this is how we're going to define this. Apparently, this one depends on what the W is. Okay, and this is how we're going to define this called the GW. Whatever W is, this GW will be just equal to the Jacobian of U at this C, such that these two sides are equal. Okay, so this G is such a function. We don't know. We actually have no idea what this G is exactly and how to write it out, but we just know that there exists such a G. Okay, and the property of G is that for any W, the UW will be equal to the U of W star plus GW and the W minus W star. So it depends on what W is. And you're going to make these two sides equal due to the, we know that this is always possible because the mean value theorem. Okay. And now with this fact, we can easily show this, this inequality because of the property of G. Since G is nothing but the Jacobian of U as somewhere between W and W star. So if we have this, we had this W star, and we have this ball with the radius eta, and we start somewhere W0 inside, then we know that within this neighborhood, all the Jacobian should have a norm less than kappa. So this is nothing but a Jacobian in the neighborhood. Okay, so the first point, if we do a connection of this, there will be some point here, and the Jacobian at this point will have a norm less than kappa. And then we move on to next point, W1, we have still within this ball, then we can guarantee that that will be the G of W1 will be will have a norm less than kappa as well. And that's the strategy here. We're going to show that this is what I have on the side, left side, will be equal to, due to the definition of this WK plus 1, it's just we just computed it by applying U to WK. And this W star is the fixed point of W of U, so its W star is just equal to U of W star, which is, since W star is a KKT point. While the difference of these two is going to be equal to this G of WK, okay, we chose the G such that this is always true, right? So this is equal to that. And then this is the matrix multiplied to a vector. As we said last previous slide, if you have a matrix A multiplied to X, it will be less than or equal to the norm of A times the X. And this A is like this G here, GWK here, and this X is like this WK minus W star here. So that's why it's less than or equal to this. And then since this G is evaluating, the G of WK is evaluating the Jacobian somewhere between, at some point between WK and W star, so it's within this ball. So that's why this one is less than or equal to kappa. And that's how I get this less than or equal to this. Okay, and now what this is a very significant result, since we can from here we can see that the distance between xk and the W star is going to decrease at a linear rate, meaning that for example, if kappa is 0.8, then you start from here. The next time, the distance between, say, W1, the distance here will be less than or equal to 0.8 of this distance. And then next time, this third one will have, this is the W1, this one will be less than or equal to 0.8 of this second distance. Okay, and then the distance is just going to decay to 0 very quickly. Okay, now with the proof we just finished for the Lagrange algorithm with for a problem with the equality constraint, equality constraints, we can quickly go over the Lagrange algorithm for inequality constraint optimization, and because the proof is pretty similar. Okay, so for simplicity, let's consider the case where only the inequality constraints appear in the problem. So we're minimizing f of x given a subject to this gx less than or equal to 0. So this is the vector valued function. and you know that the Lagrange function is going to be this, and because this is an inequality constraint, so this mu will be the Lagrange multiplier or KKT multiplier, and it needs to be greater than or equal to 0. Okay, so recall that the Lagrange condition will be just this. This is similar as you take the gradient of this with respect to x, you get that first line, and then this is the original inequality constraint. This mu is the Lagrange multiplier or KKT multiplier, which needs to be greater than or equal to 0. And then finally, the G and mu need to satisfy the complementary slackness. So the inner product of the two must be equal to the scalar 0. Okay, and this means that if Gi of x is smaller than 0, strictly smaller than the 0, then the mu I must be equal to 0. The corresponding mu I must be equal to 0. Okay. All right, so now the Lagrange algorithm in this case will be very similar to the previous Lagrange algorithm, except that we need this multiplier to be non-negative. And the only change we're going to make is to, you call this is the gradient ascent step with respect to mu. And after we compute that, we do a projection, or we take the positive part of this vector. So what I mean by that is this just takes the maximum of the argument vector at 0. So for example, if you have, say, 3 and -5, then you take the positive part will become 3 and 0. So if it's already greater than 0, then you just keep it, and if it's less than 0, you just make it 0. That's what it means. So you apply this component wisely. Okay, so the only change we made is that this is still the first Lagrange condition, which is this. And this one here, or sorry, this one here, this is the Gx, which is this one here. And the only difference is, as I said, we add this plus. So once we got a vector, all of this, then we set all the negative components to 0. Okay, so that's the only difference compared to the previous Lagrange algorithm. Okay, and the reason is obvious. We need this to be greater than equal to 0 every time, okay, every iteration. Okay, so now with this change, we're also going to make the similar notation as before. This UW, the W is the concatenation of x and the Lagrange multiplier mu. Okay, and previously this is lambda, but right now we have the mu here. The size or the dimension of mu is p, which is the dimension of the inequality constraint function g. Right, and then the UW is the same as before. It's exactly the same as before, except that this G H is replaced by G now, and the multiplier is lambda is replaced by mu here. Okay, so everything else is the same. But there's the only difference with that is that the second argument, the mu, once you computed it, it needs to make the maximum, makes the positive of it. So let's consider another function. We call it the pi. Pi of w is the you keep the x, so the w itself is x and mu. You keep the w and you make this positive of mu here. You keep the x and you make this mu positive. Or so why we use this? We use this notation earlier in this chapter to denote the projection onto a convex onto a set omega. And this set right now is that the set is Rn by Rp plus. So that means the first n components, which is this x, can be anything. This mu needs to be a non-negative vector. Okay, and that's how we set this projection to to this set. So if you have a negative vector will project to the first quadrant, you just need to make all the negative components 0. Okay, so that's actually a projection onto this space. So if you have any vector, just project it into this by making that. Okay, and now you can see this Lagrange algorithm is nothing but just the wk plus 1 equals to pi of uwk. Okay, so the only difference is that the additional pi, which is defined by this. And it's easy to show that the W star is a KKT point if and only if it is a fixed point of pi u, meaning that it satisfies this. Okay, so W star is a KKT point if and only if the W star equals to pi of u of W star. Okay. Now the complication also comes from the fact that when we reach to the KKT point W star, some of the constraints are active at W star. Some of the constraints are inactive. So what do we mean by that is if W star is a KKT point, then you can check the GW star. You see that some of the components of G are actually equal to 0, and some of the components are less than 0. Okay, because this one has to be less than equal to 0. It's a vector less than equal to 0. So some of the components are equal to 0, some of them are less than 0. The ones that are equal to 0 we call the constraint active. Right? This is what we learned in I think 2 chapters earlier. We can partition the values of GIs into 2 groups. One group is all the GIs at this point is equal to 0, and all the others are the value less than 0. Okay. And then we see that this part is P1, has dimension P1, and this one has a dimension P2. The sum of them is equal to P, which is the dimension of G. Okay. Remember that we make this active constraint, inactive constraints. This A means active, the I means inactive. We make this change, we make this partition or make these 2 categories because if it's active, then it's pretty much like the equality constraints we considered earlier. And if it's less than 0, then we pretty much can ignore it. The reason is, say we have the active constraints that are given this. So if your point is actually on this constraint, then say this side is g of x greater than 0. On this line is gx equal to 0. And inside you have gx less than 0. Okay, and you need to guarantee that it's on this side. As long as it's on this side, it will be fine. But if it's on the point, on this line, gx equal to 0, then it's like the gx is an equality constraint to this point. And if the point is here, then, since the g is continuous, then there will be a neighborhood such that the gx is always negative there. So it doesn't matter what this g is, or what these gi's are. So that's why when the g is inactive, it's like this case, then we basically can treat this is not there, okay? Because we only care about the local behavior of the point, and locally the gx is always negative around it, and the constraint is always satisfied for this inactive GIs. Okay, so, and this is important so that we can derive our proof pretty easily. Okay, so now we have the G functions that are partitioned into 2 groups. One is the G active ones and G is inactive ones. Let's just move all the active ones to the top, and all the others are to the bottom. Then corresponding to this GA and GI, there will be the multipliers mu A and mu I. Okay, remember, because we have the GX is multiplied to mu. Now I partition the G into GA and GI. The mu should be partitioned accordingly into mu A and mu I. And again, this has P1 components, this one has P2 components. Together, they have the P components, right? And now as we said earlier, it's like only the active constraints are making a difference or making some effect that we need to be careful. The inactive constraints don't really matter right now. So let's put this UA, mu A part together with X, and we form this WA. So originally W is like this X, this mu, and then we partition the mu to mu A and the mu I, so the active and the inactive ones. And now this WA is just the first two, it's just the X and the mu A. And delete this mu I. Delete this mu I component. That will be our WA. Okay, so that's the WA. And then we also define the mu A, the UA. The UA is going to be applied to the WA. And this UA, it's like right now we just ignore all these inactive constraints and we put this as equality constraints. And together with X, and then we do everything similar to similar as before. The U of W becomes UA of WA, and this will be the equality. This will be the the U of UA function. So it's the same as before. Everything will be the same as before, except that the G will be replaced by GA, mu will be replaced by mu A, and also bottom line this was mu plus alpha G. Now it's just mu A plus alpha GA. Okay, recall that. This was this. Used to be this, then we just consider the positive part. So what this one is? This is this is also a vector value function. Originally, U is what's that? U of W. Sorry, we'll actually say it in this way. So it's U is mapping from Rn plus P. P is the number of inequality constraints in G, the total number of constraints in G, and it's mapped to n plus P. Right, this is what the original U is, like here. Okay, and what it does is to map this W to U of W, and now you have a new UA. The UA is mapping from Rn P1 to Rn plus P1, and what it does is to map this WA to the UA WA. And how this WA is composed is this. Is this one. Okay, and then we can again check the Jacobian of this. It will be n plus P1 by n plus P1 matrix. And that is similar as before, right? Because that is the same as before, except that this used to be H for the equality constraint case. And then similar as before, so again, I should have removed this. So again, similar as before, we just need to make sure that the Hessian of the L with respect to X star, this is a positive definite matrix. Remember that this matrix is n by n. Okay, and again, we're going to assume that the step size is kept as a constant alpha, and we again define the G such that the G is to satisfy the mean value theorem, such that this U of WK minus U of W star. So this is always fixed, and then for any WK, there will be some point between WK and W star, such that the gradient or the Jacobian of U at that point will be here, so that these two sides are equal. But now that function is just replaced by this G, which we don't know the exact formula, but we just know that for any WK, we can find such a matrix. Okay, and it stands for the gradient, the Jacobian of U at some point between WK and W star. And then we also check the M. When we evaluate the Jacobian matrix of U or UA, evaluate this at the point W star A, that will be our M here. So in that case, the X star will be here, lambda mu A star, right? All those things will be similar as what we did for constraint equality constraint case. The G will, for the G, we only keep the active part. Okay, so that will be your M matrix. And then similar as before, we can show that if this, as long as this is a positive definite, this M will have all the real part of all the eigenvalues of M will be negative. And then we know for alpha small enough, this I plus alpha M will have a norm less than 1, smaller than 1. Okay, and these are all the same as before. And for the mu I star, we know that the gi are less than 0 at x star. So that means that the corresponding mu I star must be equal to 0, since we have the complementary slackness for each of these gi is less than 0. The corresponding mu I must be equal to 0, right? That's the complementary slackness. So that's what we know. And again, similar as before, we're going to make a few claims, and these claims will give us the convergence of the algorithm. Okay, and we're going to talk about that from here.